Hello everyone and welcome to another lesson. We're going to be graphing rational functions in this lesson, so pay very close attention and write down everything that I write down because the way I graph these is how I expect you to graph them on your chapter test. So step number one is going to be to reduce the function if possible. On this one, you can't reduce the function at all because you can't factor the numerator or the denominator, nor can you simplify from top to bottom by canceling any terms, so this is as reduced as our function gets. So now we're going to determine three things. We're going to determine if there's any vertical asymptotes, if there's any horizontal asymptotes, and if there's any removable discontinuities. So please write that down. The vertical asymptotes and the removable discontinuities we can do without using our graphing calculator. Our vertical asymptotes is when our denominator equals 0. So when does x minus 2 equal 0? When x equals 2. There's your vertical asymptote. It's when x equals 2. We draw these in a vertical line on our graph, and we dot that line. So here's our vertical asymptote. Draw it in with me. X equals 2 is our vertical asymptote. All right, the last one, our removable discontinuity, is found when any terms canceled from numerator to denominator. We didn't have any cancellations, thus we have no removable discontinuities. There are none. So now our horizontal asymptote, we have to do that by using our graphing calculator. So everyone, let's take out our graphing calculator and let's put this in our graphing calculator. One thing I want you to be aware of, when you do this, you need to tell your calculator where the numerator is and where the denominator is. So when we graph these, put the numerator in parentheses and put the denominator in parentheses. I'll show you how to do that right now. Take out your graphing calculator, press y equals parentheses x, close parentheses, we're telling our calculator what goes in the numerator, divided by parentheses x minus 2. We're also telling our calculator what goes in the denominator. Close the parentheses, and now we're going to press graph. And here's what the function looks like. Kind of unique, is it not? I want you guys to notice something. Our vertical asymptote we said was x equals 2. Look at what our graph approaches but never ever touches. It's the line x equals 2. So there's the first sign that we did it right. Our horizontal asymptote, can you guys see that it looks to be about right here? Right? It's a horizontal line that my graph approaches but it never ever touches. The way we do this, the way we find our horizontal asymptote, is we look in our calculator and we see what number the graph approaches by looking at the table. So press second, graph, because there's our table. And I just want you guys to scroll up for a while. It gets closer and closer to what number? 0.5, 0.6, 0.67, 0.71, 0.75. It's getting closer and closer and closer to what number? It's getting closer and closer to 1. But class, guess what? It's never going to reach 1. It gets closer and closer and closer to it, but it's never ever going to reach 1. I could press up until my batteries go dead in my calculator, and I'm never going to read the number 1 here in my y column. It always gets closer and closer and closer. I could also go negative, so go down, 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 and it's getting closer and closer and closer to 1 again. Notice how it's going 1.4, 1.3, 1.25, 1.22. All these y values are getting lower and lower. They're getting closer and closer to 1. But I promise you, you can press that down button forever and ever and ever, and you're never going to read the value of 1 in that y column. That is our horizontal asymptote. So that's what we're going to write down on our paper here. Our horizontal asymptote is the line y equals a positive 1. We're also going to put that on our graph paper in a dotted line. Y equals 1 is this horizontal line. Okay, so now that we have our asymptotes, what we're going to do now is we're going to sketch our function. And the way I want us to sketch our function is you're going to pick 2 points to the right of your vertical asymptote, you're going to plot them, and you're going to pick 2 points to the left of your vertical asymptote, and you're going to plot them, and then you're going to sketch the rest of the graph. So, we're going to look at our table again. 2 points to the right of our vertical asymptote. Usually go closest to the asymptote. Notice we had an error at the number x equals 2, because that's where our vertical asymptote is. See, class, right here is what I'm talking about. We have an error at x equals 2. And so we're going to graph the 2 points closest to that error. So 3, 3 we're going to plot, and 4, 2. 3, 3, and 4, 2 put on your paper. Right 3, up 3. And the other one was right 4, up 2. And then we're going to sketch the graph, and the graph looks something like this. It approaches our horizontal asymptote, and it approaches our vertical asymptote, but it never crosses them. Okay? It gets closer and closer and closer to them, but it never ever crosses them. We also want to pick 2 points to the left of our vertical asymptote. So go back to your table, and let's pick 2 points to the left of our vertical asymptote. Again, those are going to be the 2 points that are closest to my asymptote, which are these 2 points right here, at 0, 0, and at 1, negative 1. 0, 0, 1, negative 1. And then we're going to sketch our graph. So it looks like this. Gets closer and closer and closer to the asymptotes. It never crosses them. It never ever touches them. And there's what I expect from you on every single one of these that we graph. Tell me what these 3 are. Put the asymptotes on your graph. Pick 2 points to the right of your vertical asymptote, 2 points to the left of your vertical asymptote, and then graph it. And notice how your picture of your graph, your sketch here, should look very similar to what we have on our graphing calculator. Okay? This, hopefully, looks very, very similar to what we have on our paper. Okay, so there's a good check. Let's try another one, shall we? On this one, the very first step is to reduce any factors that we can. So let's factor. F of x equals x minus 3 times x plus 3. The numerator is the difference of 2 squares, divided by x plus 3. So now we have factors that can be reduced here and here. So now our reduced function is f of x equals x minus 3. So if we look at this class, once we reduce our function, we're going to determine if there are any vertical asymptotes, horizontal asymptotes, or removable discontinuities. Our vertical asymptotes are found in the denominator of our reduced function. Well, our reduced function class doesn't even have a denominator, does it? Our denominator canceled with the x plus 3 in the numerator. So we don't have a denominator, thus we do not have a vertical asymptote. There are none. However, we do have a removable discontinuity. We have a term that factored, and that was this x minus 3 term. Or x plus 3 term, rather. Sorry about that. So that means that x plus 3 equals 0, our removable discontinuity, happened at negative 3. So x equals a negative 3, there's going to be a hole in your graph at that spot. Your horizontal asymptotes, you use your calculator for. So let's put this in our calculator. In class, we always, always, always put in our original function. Do not put in the reduced function in your calculator. It's always going to be the first function that we see. So x squared minus 9 is going to go in parentheses. Y equals x, parentheses, x squared minus 9, close parentheses, divided by x plus 3. Oh, and I made a mistake, didn't I? I didn't put the x plus 3 in parentheses. And it ruined our graph. Sorry about that, class. So parentheses x plus 3. That is what we should see. And it looks like a line, doesn't it? And the reason why it looks like a line is because our factor in the denominator canceled, so our reduced function should look like this. And this is y equals mx plus b. So it has a y-intercept of a negative 3, 1, 2, 3, and then our slope is a rise of 1 and a run of 1. So up 1 over 1, up 1 over 1, up 1 over 1, so on and so forth. There is what our rational graph looks like in this one. Now I want you to notice something here. Our horizontal asymptotes, is there a horizontal line that our graph approaches but never ever touches? No, there is none. However, we talked about this removable discontinuity at x equals a negative 3. Our graph on our calculator doesn't necessarily show this, however our table does. Go second graph and look in the table. Go to a -3. Oh man, look at that. There's an error right there, which means there's a hole at a -3 on our graph. So you have to put that in our graph. So even though our calculator doesn't necessarily show that there's a hole there, you have to know that. So go to -3. Here's a -3 on your x-axis. Wherever your graph is, which is right here, you got to put a hole there. So at -3, there's a hole. And then your graph continues. So that is what this picture looks like on problem 2b. There's a hole at x equals -3. And now you're done with this one. All right, let's try another one. Here we have 2c. We're going to reduce our fraction, so f of x equals x minus 7 over x minus 7 times x minus 3. We're going to reduce our function, because these x minus 7s reduce, so f of x now equals 1 over x minus 3. Once our function has been reduced, you can now determine of any vertical asymptotes and removable discontinuities. Our vertical asymptote is when our denominator equals 0, so that's when x equals 3. Our removable discontinuity, or our hole, is when there is canceled factors, which is the x minus 7. So that means x equals a positive 7. At a positive 7, there's a hole in our graph. Let's put in our vertical asymptote right now, x equals 3. Here's 3. Draw a vertical dotted line, because that's going to be our asymptote that our graph approaches, but never ever touches. Now let's put the rest in our calculator. In class, again, you're going to put in the original function into your calculator. So parentheses, x minus 7 in the numerator. Divided by parentheses, x squared minus 10x plus 21. So when we graph this, the first thing we should notice is we should notice an asymptote at x equals 3. And there it is. There's our asymptote at x equals 3, so that's good to see. So now let's determine where our horizontal asymptote is. And what does it look like, class? What does it look like our graph is approaching but never ever touches? It looks like it is the graph, or the line y equals 0. And you can check that in your calculator if you want to. To save time, I'm just going to tell you it's the line y equals 0. So our horizontal asymptote is y equals 0. Your asymptotes, class, will always be an integer when I give them to you on a test. Your asymptotes will always be integers. It'll never be like y equals approaches 1.5 or something like that. It's always going to be an integer. So there's your asymptotes. Now what you're going to do, class, is you're going to graph 2 points to the right of your vertical asymptote and 2 points to the left of your vertical asymptote. So go to where the hole is, or the asymptote is, which is x equals 3 on your table. And here are the 2 points that you're going to plot to the right of your vertical asymptote. Here's your error at x equals 3, so you're going to plot the points for 1 and 5 and 1/2. 4, 1, 5.5. 4, 1, and 5.5. So there we have it for this one. And then 2 points to the left of your vertical asymptote are going to be 1, -0.5, and 2, -1. 1, -0.5, and 2, -1. And then your graph is going to follow along these asymptotes. They're going to approach them, but they're never ever going to cross them or touch them. Okay, we're almost done. We need one more thing. We got to tell our graph where our hole is. And our hole, why did I put, our hole, our removable discontinuity is at x equals 7. So on your graph, when x is 7, which is right, if 5, 6, 7. It's right in this area. There's going to be a hole there. So what you're going to do here is you're just going to erase that part at x equals 7. Draw a hole where you think that blue line would go through. So at x equals 7, there's a hole right there. And then your graph is going to approach that hole. It's not going to touch it. It's going to start up on the other side and continue on. So tell us where that removable discontinuity or where that hole is. I will dock you on a test if you don't put that hole in your graph. Okay, you guys pause the video and you guys try the last one on your own, please. So we have 4 over really x minus 1 times x minus 1, but there's no factors that canceled or anything like that. So this is as far as we can reduce it. So we have our vertical asymptote and our horizontal asymptote and our removable discontinuity. Our vertical asymptote, there's 2 factors, but just one asymptote because they're the same factor. So it's the line x equals 1. And there were no terms that canceled, so that means there is no removable discontinuity. And then when you put this into your graphing calculator, you got the horizontal asymptote of y equals 0 when you did this. So there's your horizontal asymptote. Your vertical asymptote was x equals 1. So there's your vertical asymptote. And then you got more of a volcano type looking thing. You should have got 1 point to the right of your vertical asymptote at 3, 1. And then you should have got the other one at 2, 4. So here is one part of your rational function. They get closer and closer and closer to the asymptotes, but they never ever touch them. And then it's symmetrical on the other side, so at 0, 4, and at negative 1, up 1. You should have those 2 points on your table. Whoopsie. So here is the other part of your graph. And that's what we have on that one. And there's no removable discontinuity, so we don't have to put any holes on that one. So that's graphing rational functions. Be sure to let me know if you have any questions on that when you get to class tomorrow.